Welcome to this explainer. Let's be honest, when most of us hear the word derivative, our brains probably immediately jump to chalkboards covered in complex, totally unsolvable equations. But today, we're going to completely strip away all that intimidating academic jargon. We are going to uncover an incredibly intuitive tool that literally explains the world around us. Because at its core, a derivative is really just a language for describing change. It doesn't just tell us how much something changed, it tells us exactly how fast it's changing right now, in this very moment. Okay, let's dive into this by picturing an everyday object and a really specific problem. Imagine you're on a road trip and you travel 120 kilometers in exactly 2 hours. Well, it's pretty easy to say your average speed was 60 kilometers per hour, right? But here is the catch. How does your car, or, a highway patrol officer with a radar gun ready to hand out a speeding ticket, how do they know your speed right at one specific split second? And that right there highlights the fundamental flaw of averages. Think about your drive. You absolutely didn't drive 60 kilometers per hour the entire time. You probably stopped at a red light, maybe got stuck behind a slow-moving truck, and then sped up to 90 for a bit. An average rate just isn't going to cut it when we need to know the rate of change right in the present moment. We definitely don't want to wait a whole minute or a whole hour just to figure out how fast we're going. Now, the speedometer on your dashboard actually solves this exact problem of now. It doesn't care about your whole trip. Instead, it keeps shrinking the time interval it's measuring, making it smaller and smaller until it approaches the very meaning of now. And this specific problem, trying to capture the instantaneous rate of change, is the gateway that leads us directly into derivatives. Let's actually slow down the pace for a second here to visually translate this math. Just imagine a curve on a graph that shows your distance over time. If we pick two distant points on that curve and draw a line right between them, we get an average rate of change. But if we take those 2 points and physically move them closer and closer together, that average suddenly becomes a much better description of what is happening at one very specific location. We are essentially shrinking that gap until it becomes a single, frozen moment in time. Watch what happens as those points move closer together. As the gap shrinks, that line connecting the 2 points, which is called a secant line, transforms. It becomes a precise tangent line that only touches the curve at one single point. And the slope of that tangent line, that is your instantaneous rate of change. That is your derivative. Which brings us to this. This is the formal limit definition of a derivative. It measures how much your output, or your y, changes compared to an extremely tiny microscopic change in x. Now, I know this looks like a terrifying wall of mathematical notation, but please do not panic. The math is quite literally just a translation of the visual we were just talking about. In fact, whenever you come across that scary formula, I just want you to read it in your head as this simple, plain English sentence. Move the 2 points closer and closer, then read the slope of the curve at that instant. That's it. It just asks one tiny question. What happens if x changes by a tiny amount? Slope, rate of change, and instantaneous speed, they are all just different faces of the exact same idea. So the real magic here is that by applying this rule, we completely change the question we are asking. If we have an equation for the position of a car, taking the derivative mathematically turns that position into speed. If you plug in a specific time, say 3 seconds, the derivative tells us the car is moving at exactly 8 meters per second. The derivative changes the question from where is the car to how fast is it moving right now. Let's ditch the equations for a minute and become storytellers. Just by looking at the slopes of a curve, we can read its story without needing any complex numbers at all. The sign of the derivative, whether that slope is pointing up, down, or totally flat, tells us the entire direction of the narrative. It basically boils down to 3 simple states. If the derivative is positive, the curve is rising and your quantity is increasing. If the derivative is negative, the curve is falling and the quantity is decreasing. And if the derivative is exactly 0, well, you've hit a smooth peak or a valley. It's a turning point where the slope is totally horizontal. These simple little states help us instantly answer major real-world questions, like figuring out exactly where improvement begins or where a decline starts. All right, let's pick up the pace and zoom out to see derivatives in the wild. Think about a roller coaster. 2 points on a track can be at the exact same height of the ground. But one point might be on a perfectly flat section, while the other is right in the middle of a terrifying vertical drop. Height clearly isn't the whole story here, so why does the slope matter so much? because the motion feels completely different to the riders, and that is entirely due to the slope. Engineers care deeply about how quickly the track's height changes with horizontal distance. A large slope means a really rapid change in height, while a slope near zero means a much flatter track. By using derivatives, engineers can feed this math into massive models to calculate speed, acceleration, and most importantly, keep riders comfortable and safe. Okay, how about another everyday scenario? Consider your morning coffee. The thermometer says it's 60 degrees Celsius. But just knowing the temperature doesn't tell us everything about its current state. Is it fresh out of the pod and dropping rapidly? Or has it been sitting in a thermal mug for an hour and is almost completely stable? The temperature alone just can't tell you. But if you combine the thermometer's current reading with the cooling curve's derivative, it reveals the secret. The derivative tells us the exact rate the temperature is falling. If the derivative is negative, well, we know it's cooling down for sure, and the larger the magnitude of that number, the faster the cooling. It tells us exactly what's happening, in degrees per minute, at that very instant. Now, this concept isn't just for physics geeks or thermodynamics. It is heavily used in business and economics too. Say you're a business owner trying to maximize your profits. How can you use this exact same invisible math to find the perfect price point or production level? Really, where exactly does the best decision lie? The answer becomes super clear when we look at optimization. The best decision usually lies exactly where growth stops. If you're looking at a profit model curve, you want to find the exact peak right before profit starts to decrease. You do this by finding where the derivative equals zero. The derivative doesn't create the profit, obviously, but it acts like this powerful radar to pinpoint the maximum potential inside a business model. All right, time for a super quick, rapid-fire check to test your understanding before you go, trying to memorize any textbook rules. Ready? If you know a car's position, its derivative is the instantaneous velocity. A negative temperature derivative? That means your coffee is cooling down. The derivative at the absolute peak of a profit curve? Zero. And the derivative of water volume over time? That would be measured in liters per second. See, you already intuitively understand the real, practical questions that derivatives answer. Let's move to the big picture now and see how this builds by adding one final layer. Since speed itself can change, like a car accelerating from 20 to 60 kilometers per hour, we can actually take a derivative of a derivative. It's like inception. By differentiating a second time, we find the acceleration. This tells us not just how fast something is moving, but how its speed is actively changing. And that is absolutely central to mechanics, robotics, and physics. So what we've seen today is that a derivative is way, way more than just an annoying chapter in a high school math book. It is literally a universal language. It's the language environmentalists use to measure changing pollutant concentrations. It's how AI algorithms find directions to reduce errors. It's how doctors track drug concentrations in human biology. It is the fundamental way we measure how states move and change in the universe. We've seen how the invisible math of calculus governs the everyday things all around us. So I want to leave you with this provocative thought. If a derivative perfectly describes the speed and direction of change at every single instant, what in your world is changing right now, and with respect to what? Take a look around. You might just start seeing the math everywhere. Thanks for learning with me today in this explainer.